Welcome to week 3 of hazardous waste treatment and disposal. This week we're going to discuss the basic chemical and physical properties of hazardous waste. Many of the topics mentioned this week are general in nature and applicable to a wide variety of fields and applications, so I encourage you to think of the big picture and not necessarily only focus on hazardous waste. Just a reminder that this audio will only cover some of the more important or confusing aspects of the video presentation, and the textbook covers all this material in much greater detail. Different concentration units are used to quantify the concentration of hazardous chemicals, depending on whether they are present in water, solids, or air. Most concentration units are some form of mass per unit volume or mass per million units, which is often expressed as parts per million, ppm, parts per billion, ppb, or likewise. Two common concentration units used to quantify the concentration of hazardous chemicals in air are the micrograms of contaminant per cubic meter of air and the ppm unit of 1 part contaminant per million parts of air by volume. One concentration unit not mentioned in great detail but used often in hazardous waste work is the pH unit. Basically, water can dissociate to a slight degree, or another way of saying this is that the water molecule has the ability to break into some H+ ions and an equal number of OH- ions. Under standard conditions of temperature and pressure, water would have a concentration of 0.0000001 moles per liter of H+ and an equal amount of OH-. Expressed exponentially, this would be stated as 1 × 10⁻⁷ power. pH stands for the negative log of the hydrogen ion concentration, which translates into neutral water having a pH of 7. Since pH is a logarithmic scale, the key to remember is that a unit change in pH, like going from 7 to 6, means the hydrogen ion concentration has increased by a factor of 10. Likewise, a unit change in the other direction, like going from 7 to 8, means the hydrogen ion concentration has decreased by a factor of 10. I mentioned the word moles a moment ago. A mole is a scientific term for the weight of a large but fixed number of atoms or molecules. The periodic table is a tremendous help here, as each element has the atomic weight in numbers next to the elemental symbol. An elemental mole would be the atomic weight. So 1 mole of carbon weighs about 12 grams, and 1 mole of oxygen would weigh about 16 grams. And the weight of 1 mole of carbon monoxide, CO, would therefore be about 28 grams. The mole unit is often helpful when trying to determine the mass of something that will react with the mass of something else. Flash point is a concept of significant importance in the determination of hazardous waste. Flash point is defined as the minimum temperature at which a compound emits sufficient vapor to form an ignitable mixture with air. Basically, how much do you have to heat something before it can catch fire? It was mentioned in a previous week that due to the complexity of chemical bonds with organic chemicals, that there are a tremendously large number of organic compounds possible. Given that we have different common names and trade names and different foreign languages throughout the world, a numerical system or registry has been created to number chemicals. This registry is known as the CAS registry and lists CAS numbers. Each CAS number refers to one and only one chemical. Therefore, an American can refer to a chemical by its CAS number and be ensured that someone in Japan knows exactly what chemical is being discussed. A material or mass balance is a way of merely describing that the accounting needs to be able to explain where all the material went. If I have paperwork showing that I gave you 10 tons of benzene, and when you disposed of the benzene, the final paperwork confirms that 9 tons were processed, then the mass balance would show a discrepancy of 1 ton. Not good. The amount of material at the beginning should be the same as the amount of material at the end, even if the form or physical condition has been changed. Hazardous waste sites must be assessed to determine the extent of contamination before cleanup is initiated. Part of the trouble with the assessment is that hazardous waste disposed of improperly at waste sites are not usually evident to the bare eye because most of the contamination is below the soil surface. Therefore, a series of site assessment procedures must be conducted, ranging from record searches to very thorough subsurface sampling. Sampling of materials including contaminated soils, sludges, lagoons, or drums is often necessary to assess the degree of hazard and to comply with regulations. The sampling must be performed to documented protocols and follow statistical principles for accurate information. Sampling may seem like an easy event, but consideration must be given to being able to document a representative sample, an uncontaminated sample, a proper chain of custody for legal proof during analytical analysis, and all the time ensuring personnel safety in a potentially hazardous area.